Kia ora tātou. Welcome to the Fire Emergency New Zealand's Risk Reduction Continuing Professional Development Series. This module is on Scion's Fire Research Program. It is designed to build your foundation knowledge in this area. Today's presenter is Grant Pearce, Scientist in Fire Research at Scion. Welcome, Grant.
Yeah, thanks very much, Trent, and good morning, everybody. And thanks for the opportunity to talk to you about the Rural Fire Research Program. So I'm Grant Pearce. I'm a senior scientist within the Scion Rural Fire Research Group. I've been with the program since it was first established back in the early 1990s. So have a long history of researching all aspects of rural fire. I guess particularly around fire behaviour and fire danger rating, as you'll see as we go through the presentation. But also I have a real interest in the fire weather and fire climatology area as well. So my background is in physical geography, and so I guess hence the interest in the natural environment and the weather and atmosphere and in vegetation and fuels and how that all comes together in fire. So on completing my master's degree, I was employed by the then Forest Research Institute to, I guess, get this fire research program started. And have continued to research, as I say, a range of aspects of rural fires over those almost 30 years. So I guess in that time I've been involved in the research, but also in operations, so in terms of supporting the rural fire authorities and fire service, and now Fire and Emergency New Zealand. And I've also been involved in an operational capacity overseas, particularly in Australia, assisting with fire behaviour prediction for some of the major fires over there during the mid-2000s in particular. All right, so I guess enough on me. So I guess first up, who's Scion? So Scion is really just the trading name for the New Zealand Forest Research Institute. It's one of the Crown Research Institutes, along with the likes of Landcare and NIWA and Ag Research and the like. Originally began as the Forest Research Institute under the New Zealand Forest Service, and now has about 350 staff, with our main office in Rotorua at a small office in Christchurch with about 25 staff and a small sub-office in Wellington as well. And what Scion does is it does the research around forestry and wood products. And that includes biosecurity and risk management, which is where fire sits within the programs within Scion. And the reason that the Rural Fire Research Program is based at Scion is largely historical. There was fire research undertaken during the New Zealand Forest Service era, based out of FRI, the Forest Research Institute in Rotorua. And that really was about research to support the controlled burning that was being done by forestry at that time. But it also included adoption of the Fire Weather Index system from Canada, which is the basis for our fire danger rating system here in New Zealand. So there was a gap of around 15 years between sort of the research under the Forest Service and then the new program being established in 1992. And then it was relocated from Rotorua to Christchurch in 1998, and we've been based here ever since. And fire research started as a very small program with just 2 full-time staff, and we've expanded over the years, and we're now a team of sort of between 6 and 7 full-time equivalents, so spread across a number of staff. So looking at some of those in the team, some of these names you'll recognise, so as well as myself and Veronica Clifford there, who presented the last presentation. We also have a mix of social science, human factors and ergonomics, and atmospheric modelers, as well as technical support. And then in addition to the core people within the team, we also then involve other staff from across Scion, depending on the projects, and then also casuals and seasonal staff as well. And obviously, we can't do all of this research on our own, so we do significant collaboration with external organisations as well. So that includes the other Crown Research Institutes like NIWA, for example, but also, particularly in recent years, the University of Canterbury, and then internationally with the likes of the Bushfire and Natural Hazards, CRC, but also currently the US Forest Service. So I guess, what are the aims of the Rural Fire Research Program? Why are we here? Well, our mission statement is to develop the science and technology that's needed to support and protect life and property and manage fire in the rural landscape, and to provide fire and land management organisations with improved information and capacity to better enhance firefighter safety, understand fire behaviour, continue to allow the safe and effective use of fire as a land management tool, deploy effective firefighting resources, manage fire in different landscapes, and in recent years, particularly focusing on increasing community resilience to wildfires as well. So where do we get our funding from? So most of our funding comes through the New Zealand government, through the science and research funding streams. So we're currently in year 4, or just finishing year 4 of a 5-year MBI Endeavour funded program, preparing New Zealand for extreme fire, and just working on what might make up the content of a new bid that we put to government for continued funding. Parts of the program are also funded by the Resilience to Nature's Challenges National Science Challenge. That's particularly the social research around community resilience. And then we're also supported by the rural fire industry through co-funding provided by, of course, Fire and Emergency New Zealand, but also through the likes of the Forest Growers Levy Trust, from the Department of Conservation and from the New Zealand Defence Force, and then also additional in-kind support, particularly from the likes of Federated Farmers. And our total budget currently is a little over $2 million per annum, supporting those 6 to 7 full-time staff and operating costs. In terms of governance and strategic direction for the research, we have the support of our Rural Fire Research Advisory Committee, which includes representatives from those funding organisations, Fire and Emergency, forest owners, DOC, Defence, Federated Farmers, and also local government. And their role is to provide strategic direction in terms of research needs and priorities, governance in terms of program oversight, in terms of how we're progressing against annual work plans and budget, and where necessary, being able to provide additional in-kind support to ensure that we can conduct the research. And that role of that group is covered by a collaboration agreement. All right, so into the main presentation. So I guess what I'd like to do today is just work through the different parts of the program. As I said, that aligns with the funding and where that comes from. So I'll start off by talking particularly around sort of the government-funded research, and then move on at the end to talk more about some of the other additional operational research we do, and also how that feeds into the tech transfer that we're doing to get that information out to the fire sector where it's needed. So fire research began in 1992, as I said, and much of the focus of that early period of the research was on developing the New Zealand Fire Danger Rating System and models for predicting fire behaviour in New Zealand fuel types. So a real focus of the program at that time was on experimental burning, documenting wildfires, and then taking that information and using it to develop fire behaviour models. So particularly validating some of the models from overseas, so within the Canadian Fire Behaviour Prediction System, but then for our unique vegetation types, particularly our scrub fuel types and even tussock grasslands, developing unique New Zealand models for those fuel types. And it was really right from the outset in that early period that there was a strong focus on technology transfer and making sure that the research wasn't being done for research's sake, that it was being used and applied and taken up by the sector. And so there was a real focus on a whole range of different mechanisms of getting that information out, particularly through publications, but also through training and the sort of face-to-face engagement with the sector as well. But I guess if you had to sum up that period, most of the focus was on developing the underlying models and systems that sit behind many of the tools that we currently have today. So there was a huge effort, as you would have heard from Veronica's presentation around the fire environment, about understanding the New Zealand fire environment and describing and quantifying it, developing these models for quantifying fire behaviour, a focus on understanding productivity and effectiveness of different types of suppression resources, particularly in those early years, aerial suppression, and then working on making sure the fire danger rating system had been evaluated for New Zealand specifically and was being applied correctly within our fire environment. So a huge focus on conducting experimental burns, and over the period of about 10 years, I think we did around 120 experimental burns across something like 6 different vegetation types. And these are everything from sort of small scale burns of 50 by 50 metres up to much larger blocks of a couple of 100 metres by a couple of 100 metres, depending on the fuel type. And here the real aim was to quantify what the fire was doing in terms of its fire behaviour, so fire spread rates, flame lengths, fuel consumption, fire intensity, and to relate that to components of the fire weather index system in particular, and also then developing these models for predicting how fires would burn under different conditions. So yeah, so much of that, as I said earlier, was around validation of existing models from overseas. So that's particularly in the case of mature pine and logging slash and pasture grasslands. And then development of models for these unique New Zealand fuel types, gorse and manuka scrub, tussock grasslands, and even crop stubble. And that's based on that combination of observations from these small scale experimental burning trials, and then also documentation of wildfire behaviour as well. Because obviously there are fuel types like standing pine, where the owners of those forests aren't that keen for us to burn them for experimental purposes. So we're solely reliant on the documentation of sort of opportunistic wildfire events. And also we want to make sure that the models work under the really extreme conditions at the high end of the range. And often it's not particularly safe to be able to conduct experiments under those really extreme conditions for the risk of escape. So often you're using the wildfires to supplement data from experimental burns at that upper end of the range. So yeah, so much of the focus was on developing and evaluating the fire danger rating system. So most people are, I think, are familiar with the fire weather index subsystem, which is sort of the central core of the fire danger rating system, with the fire behaviour prediction system being the second major component. But within the sort of original Canadian fire danger rating system, there are a series of other components, the fire occurrence prediction system and the accessory fuel moisture system as well, where only limited work has really been done even to date here in New Zealand, and in some cases even back in Canada. So really it's the right-hand half of this graphic, which is where a lot of that early work was done in New Zealand. Taking the fire weather index system, validating that for the key fuel types, developing these predictive models for fire spread and intensity, etc., and then utilising those to develop things like fire danger class criteria, etc. So that was the first, if you like, period of the fire research. The second period from around 2000 really was about conducting research based around the 4 R's of emergency management to support fire risk management. So continuing to describe the rural fire hazard scape under the reduction component, further improving the fire danger rating system, including the New Zealand Fire Behaviour Prediction System under the readiness component, developing tools and guides to support operational decision making under response, and then also bringing in the new social science into the recovery space to begin to work on the how we can improve community resilience and recovery from wildfires. So much of the second period, if you like, of the research program focused on the development of tools and guides and guidelines. So there's been a whole range of tools developed over the years, and that includes everything from sort of the manual lookup tables like the Manual for Predicting Fire Behaviour in New Zealand Fuels, through to software calculators for predicting fire behaviour, through at the top right to even fire growth simulation models that work in a more GIS environment to predict the fire behaviour of the fire as it spreads across the landscape. But other tools also, including the likes of the fire weather system and its early iterations, with NetConnect Fire, and then more recently with the NIWA EcoConnect based fire weather system. So a real range of tools and guides within that period, and a huge emphasis on application of the outputs of the fire danger rating system to aid decision making. So whether that decision making was about what happens before a fire occurs in terms of setting fire season restrictions or closing areas because of high fire risk, to developing readiness systems for what resources are going to go out the door when a fire is reported, to some of these tools for predicting fire behaviour during going wildfires. So right across the spectrum in terms of the application of these tools. This was also where we first began sort of research into the firefighter aspects, so the human factors around firefighting. So starting to document resource productivity and effectiveness, including the development of an instrumentation kit that could be put on the firefighter to collect data about how hard they were working. So how much ground were they covering using GPS in terms of what distances were they walking, what sort of terrain were they walking up, how hard was the heart working in terms of heart rate, what was their skin temperature and breathing rate, what was the environment in which they were working in terms of carbon monoxide exposure, and then linking that all to a video which was able to, I guess, provide information that supported all that data that was collected by the different sensors. So able to then go back and look at what tasks the firefighter was undertaking and allocate the data to those different periods to better understand the workload and how effectively they could work at those tasks in different environments. It was also when the social research really, I think, got off the ground and had some real capability put into that space. So research around, again, understanding communities, the makeup of communities and communities that have been impacted by fire and how they responded, but also things like their awareness of fire risk and of fire danger warnings and those sorts of messaging, and what they did in response to those messages. And I think there's much more that can be done in that space as we carry on. And then we come to sort of the more recent period where one of our MBIE research programs had 4 major themes which continued that vein of research. So managing emerging risks. So what were the things that were changing in the New Zealand fire landscape? So problems like wilding pines, coming up with new and improved ways of estimating things like the seasonal die-off of grasses using satellites. What's the effect of climate change on fire dangers and fire risk, and also further improving some of the tools that we had. So taking some of the manual systems and turning them into some of the software calculators, for example, and other tools that are now available. As I said, much stronger focus, much greater focus on the social research, and under number 4 here, improving safety and productivity of firefighters, better understanding production rates for different firefighting resources, looking at how we can use new technologies like drones, UAVs, to aid with things like fire hotspot detection and fire mapping. And then the other new area of research over this period was looking at the use of fire as a land management tool and getting to the guts of the issues that influence whether fire can be used and has public acceptance, things like smoke, nuisance, etc. And also looking at the benefits associated with fire use in terms of some of the other environmental aspects, things like pest control, removal of fire hazard, etc. And this was also where we began looking at the modelling of smoke. So this a new area around fire as a land management tool was one that was really sort of kicked off during this period. There was a lot of focus on understanding how fire was being used and why, and what the associated risks and benefits were with those uses. We really didn't know up until this work was done the extent of the burning that was undertaken in New Zealand every year, and I think that's really opened fire managers' eyes in terms of how much of it is going on and what it's being used for, and therefore the risks associated with that. And then, as I said, a real focus on looking at how we could, again, look overseas to what had been done in terms of smoke modelling, and then developing a system for use here in New Zealand, and particularly looking at case studies for some of the wildfires that occurred over this period. So again, I mean, maybe I should just emphasise that what we've always tried to do here in New Zealand is look at what else is going on around the world, and rather than reinvent the wheel and come up with something ourselves here in New Zealand, see if we can pick the best out of what's being done globally, and then look to modify and adapt that where necessary to our New Zealand situation. And so the fire behaviour prediction system and the fire danger rating system is one good example of that from Canada, but also the smoke models are another example of that here, with the system being picked up from the US. And then the other area I said that really grew during this period is around the human factors and associated with resource productivity and firefighter effectiveness. So again, getting more of those instrumentation kits that have been developed out to firefighters and fire crews out working on fires, and looking at how that workload and productivity was affected by carbon monoxide. And also reviewing the productivity and effectiveness of aircraft as well as other ground resources. So there's been a lot of work done during the 1990s on helicopters and a little bit around fixed wing aircraft, and so this work looked to review that and look to update it where necessary in terms of productivity rates for different types of aircraft. But also, again, as I said, I think evaluation of new technologies like unmanned aerial vehicles, drones, their use for identifying and mapping hotspots as a substitute for the use of helicopters and really expensive high resolution infrared cameras, using these smaller drones and drone-based cameras, they were able to do that as effectively but at a much lower cost. So the potential to tap into those sorts of resources. And I think there's, again, further work that can be done in this space to look at how we can use drones to improve situational awareness for going fires as well. What are the assets that are downwind? What are the fuel types that the fire is burning in and could burn into? How can we better utilise aerial mapping from drones to then link to validation of predictions of fire spread from some of our other tools, and even to input into updated estimates of burnt area for smoke modelling. So I think watch this space. There's lots more that can be done around use of unmanned aerial vehicles. So that's sort of, I guess, a quick review of some of the work that's been done under the various MBIE government-funded programs over the years. As well as that, there's also work around sort of the creative science. So one of the aspects about getting government funding is that we have to reinvent ourselves every 4 to 5 years and show that we're doing something new and creative. And that doesn't align that well with application of the research in a more applied fashion to things like operations. So we have this mismatch, if you like, between the need to be doing cutting edge science, but also developing systems and tools that can be used operationally. So a current program called Preparing New Zealand for Extreme Fire is this 5-year program that ends in 2021. It's got 5 key areas around extreme fire behaviour, around real-time fire monitoring tools, extreme fire prevention technology, targeted protection, which is kind of a catch-all goal around bringing all the various aspects of the program together, and again a little bit more around use of fire as a land management tool, and in particular training courses for fire and land managers. So quickly just working through those themes. The extreme fire one is related to testing a new theory around the role of convective heat transfer and fire spread. And that's based around this theory that's been developed by the US Forest Service through a series of lab experiments that shows that radiation on its own is insufficient to ignite fine fuels, and that convective heat transfer is just as important and potentially more important than radiation in that ignition and spread of those fine fuels at the flame front. So here we're doing a series of burn trials over the 5-year program through this major collaboration with the developers of the theory, the US Forest Service's Missoula Fire Sciences Lab, the University of Canterbury, the University of New South Wales, and San Jose State University. So we've conducted a series of burn experiments in 3 different fuel types in crop stubble during 2018 and 2019 as the best real-world replicate for the very uniform fuels that are used in the lab experiments, through to more complicated Gorse scrub fuels just in the last year. And eventually we want to move into burning some standing wilding pines to really test this theory under the really high flame lengths and high fire intensities that we see during some of our major wildfires. And here the goals are to measure heat transfer and other fire characteristics for these spreading line fires, with the aim of improving our understanding of heat transfer and the extreme fire behaviour and fire spread mechanisms. So just focusing on the most recent burns, back in March we completed 6 research burn experiments in these Gorse scrub fuels. We were burning 4 hectare plots in this case, so 200 by 200 metre plots, with 2 burns being conducted each day, with days in between for shifting instrumentation and setting the burns up. And yeah, we're really grateful for the huge support that we had during this from our research collaborators, but also from Fire and Emergency and DOC, who provided significant staff input and suppression equipment to ensure that these fires could be conducted safely and didn't escape. And as well as those resources turning out on the burn days, the 3 burn days we had over the space of a week, we also had 3 full days of burning out prior, which again was a significant input from a lot of volunteers mainly to support these burn experiments. So we're extremely grateful for that. I won't talk too much about the results of the burn experiments because I think that would make a really good topic for a future presentation where we focus just on that. So I'll save it for then and just carry on looking at some of the other parts of our current program. So the second theme is around development of real-time fire and smoke monitoring tools. And here the objective was to take a series of standalone systems. So we had satellite fire detection systems that were available internationally. We had fire growth models like Prometheus that could predict the fire across the landscape. And then we had smoke models which could predict where smoke was going and what emission concentrations were present, etc. But they were all standalone systems with their own software, and they didn't talk to each other. And they didn't run in real time, so they weren't using the latest information. They were more scenario-based. They were more sort of post-event analysis. So this research sought to develop a more real-time integrated system that combined all of these various components, with the aim of then being able to develop something that could be adopted operationally and used to support operational decision-making about where fires were occurring, where they were likely to spread to and what assets were at risk, and then where the smoke was going, what communities might be affected and what were the public health effects of that smoke dispersion. So again, this was a major collaboration with another team from within the US Forest Service, the Air Fire team, CSIRO's Atmospheric Sciences Group, and the Canadian developers of the Prometheus software. And I guess I've talked through this, but really it was about bringing those various systems together for fire detection, for fire growth, and for smoke, starting with where's my fire and what are the fuels that it's burning in, how big is the fire and what fuels are getting consumed, how fast is the fire growing, what are the emissions, where is the smoke going, what are those impacts going to be. So it was about bringing all of those systems together, making sure that the information from one could feed into the next subsystem and so on. So this is an example of sort of a real-time fire smoke prediction based on one of the early tests of the data. So using satellite hotspots from, I think, MODIS in this case, the MODIS satellite sensor, and then running the smoke models to show where that smoke was likely to go. One of the things you may pick up if you're familiar with some of the infrared hotspots around the country is that in those early detects we also picked up the permanent features like the gas oil rigs off the coast of Taranaki and things like the steel mill on the west coast south of Auckland. So a need to sort of filter out some of those permanent sources that are always going to appear so that we're just detecting the fire hotspots. So we currently have a prototype web interface that's just in development at the moment, not quite ready to go public, but we will be trialling that system over the coming fire season, and we are talking with Fire and Emergency about how we might implement this operationally and how we link this to the operational systems like the fire and incident reporting system within the communication centres, and how we can tie in things like the 111 fire reports as well as the satellite fire detections in here as well, so that we can start to also predict fire spread and smoke for those. So just looking at an example of that, so the recent Pukaki Downs fire near Twizel that occurred in the Wilding Pines. These are some of the satellite fire detections during the sort of early stages of that fire. One of the issues being that at the moment that some of these satellites pass over New Zealand only once, maybe twice a day. So we haven't really got a real-time satellite fire detection component yet, but we are working on how we might be able to utilise other satellite systems like Himawari, which can give us information every 15 minutes. But unfortunately, it doesn't fly right over New Zealand, so we've got to look at things like correction for the angle that the satellite passes over to give us good spatially accurate information. But we are hopefully going to get to the point where we have real-time satellite fire detects that can be then linked to the fire growth and smoke, which data can then be taken out of, downloaded, and then overlaid over things like Google Earth or other operational systems. For example, within the communications centres. The third area of work currently is around developing new response technologies. So that's looking at what new tools, technologies, equipment can we develop to help support firefighting operations. So in this space, we've particularly been looking at, again, work around the UAV-based thermal sensing systems and how we might be able to extend the current system to operate during extended hours, such as during the day, rather than just overnight or in the early hours of the morning when the ground is cold, utilising other sensors such as hyper and multi-spec as opposed to just infrared. Also looking at development of quick deploy sensors that could be used to detect the presence of flame and heat out in the rural environment and provide warnings about the presence of fire. And here we've got collaborations with some of the communications providers like Take Communications, another company, in fact, here in Christchurch, which is developing these sensors as well. So it's about how can we come up with new tools and technologies that again help detect these fires and then alert to their presence more quickly so that we can respond faster and more effectively. So this fire alert sensor has been developed and trialled, and really that's just a thermocouple, so a temperature measurement that's connected to a communications package, which sends an alert when a threshold temperature is exceeded. We've been testing it with a threshold temperature of around 65 degrees C. So once the temperature reaches that, it sends a message through whatever communications network is being used, and we've tested a range from radio, communications, cell phone, satellite, and proven that the system can work in any of those environments. And then we've trialled it during some of our research burns. So tested it during this crop stubble burns, but also during the more extreme gorse burns as well. And there we've seen that if properly insulated, the sensor can survive the high temperatures and continue to provide information showing the approach of the fire, but then also as the temperature comes back down and the fire moves away. And so here, one of the options is to use this sensor with prescribed burning to place around the boundary of a prescribed burn to provide alerts of where a fire might be threatening a boundary and have potential to escape. Or they could be used and put out permanently within high value areas such as forests to indicate the presence of a fire. Or they could even be developed as a really rapid deploy sensor that could be dropped from aircraft out ahead of the fire to provide an alert of when the fire has reached that point in the landscape, which might trigger other things like evacuations. So there's a number of, I guess, options about how these sorts of sensors might be used operationally. We've also been able to link the sensor to fire suppression systems. So successfully trialled using it to automatically switch on a sprinkler system. So once that temperature was reached, that threshold temperature was reached, the system was able to turn on either the sprinklers using electric water valves, or if you had an electric start pump, you could actually use this system to trigger the pump starting as well. So if you think about a fire approaching a rural-urban interface area, if you had some of these sensors around the boundary of a property linked to some external fire sprinklers around the boundary of that property, then you could use these to trigger the turning on of those sprinklers. So that's one possibility about how we might be able to then extend the applicability of this sensor system. The other thing that we've been investigating is the use of a modified sensor to monitor the temperature build-up within piled material, particularly on harvesting skid sites within plantation forests, where here you'd be able to monitor that pile temperature remotely and provide an alert when a threshold temperature was reached, which might be an opportunity to go and cool the pile by adding water, or if necessary, open it up and try and spread the material out prior to it reaching a critical temperature when that might cause spontaneous combustion. So that's part of a broader study that we've been doing using funding from Fire and Emergency to look at what factors contribute to these fires on forestry skid sites, what environmental factors in terms of aspect and slope and weather conditions, but also what sort of harvesting practices in terms of the material, the types of material that are within the heaps, the depth of material, whether they're capped with earth, etc. Whether those different practices contribute to a greater frequency of these skid site fires. So that work is just currently being written up, and that report will be available soon. And then our fourth theme of our current program is around targeted protection against extreme fire. And really it's about bringing these various aspects of the program together. So how do we identify what's really important out there in the landscape, not only to landowners and say forest owners, but also to communities. And that includes some of our Maori communities, where their value systems are quite different than say other parts of the community. So understanding what those values are, understanding what's important and what needs to be protected. And then the second component of this is understanding what mechanisms of protection are acceptable to those different communities as well. So in the case of a plantation forest, it might well be acceptable to bulldoze a fire break around the boundary of that. But if it's a community or an environmental asset, you probably don't want to do that. So do we want fuel reduced zones? Do we want to use low flammability plantings? Can we use some of these sprinkler systems or fire detection systems, for example? I think a really other interesting aspect of this work has been working with Maori communities to understand some of their legends and myths around fire historically, and how that understanding of fire could also be built into developing some of these solutions, or how it could be used to help aid the communication of some of these potential solutions in those discussions, those conversations with those communities. And so this is work that particularly is to date focused in Northland, being done in conjunction with Te Tira Whakamataki, the Maori Biosecurity Network. We're already working in that space with communities about other threats like carry dieback and myrtle rust. So to be able to also build in discussions around fire as part of that, and local community representatives as well to help guide some of the interactions that are occurring up there. So back in August last year, we had a really great workshop and fire fair with a community near Kaio, where we were able to sort of pilot test this conversation around values. And that was really interesting in terms of getting the whole spectrum of the community, from the elders to the younger generations, and comparing their different views around what was important to be protected and what might be appropriate in terms of some of the ways of protecting that. And I think it was a real eye-opener to some of the elders within the community that the younger generations thought very strongly about protecting some of these environmental and cultural values. I think that was a real pleasing thing for some of the, as I say, the elder members of the community. As part of that, we also had, in conjunction with Fire and Emergency, a really successful Fire Fair Day, where it was built into some operational training that was being done and operating around helicopters. So they were able to demonstrate that to the community, and things like bucketing. The kitchen fire safety unit could be linked in and demonstrated to community members, activities for children, but at the same time also some of this educational information around the research that was being done, the need to sort of talk to communities and understand values and options for mitigating fire risk, and then I guess the ability for communities to want to get involved in the research in more detail. And finally, the last of the themes from the current program around fire is our land management tool. We're here, the key aspect was really about developing and running some prescribed burn training courses, particularly with high country farmers, but also stubble burners and other people that are conducting burns like forestry, where the aim here was to develop a sort of a classroom-based training component that was linked to real hands-on field-based training around getting out and conducting burns and looking at different ignition patterns and smoke management and ways of conducting these fires safely and effectively while still meeting the objectives of the burns. And I guess unfortunately with COVID, the plans around this to actually run a series of training courses have been delayed, but we will be focusing on this over the next 12 months, where we hope to run a series of courses to test the work that's gone into developing this course material and the hands-on component that can then be handed over to the likes of Fire and Emergency and forestry, for example, and federated farmers to then take out and run these courses more widely. And here we're collaborating with staff from the Nature Conservancy, which is an organisation in the US that does a huge amount of work with private landowners around prescribed burning. So they have huge expertise in training with private landowners and other agencies. And so they've been really helpful in terms of pointing us in the direction of existing course material and expertise when it comes to presentation of these hands-on type courses. All right, so that's, I guess, the core MBIE government-funded research that's currently underway. The other area of work presently is around that under the Resilience to Nature's Challenges. And so here there's a Resilience to Wildfires project as part of a broader program of community resilience to natural hazards. Within that, there's been two aspects of work, one around improving community resilience and understanding how to engage with communities and talk about shared responsibility and promote community-based planning processes for fire risk management, and also looking at volunteering, both in the traditional sense, why people are attracted to join volunteer fire brigades, but also non-traditional volunteering. So why people volunteer during major hazard events, natural hazard events, and how that can be tapped into on a more regular basis. And then a second component looking at statistical wildfire risk modelling and how we can link wildfire risk into other risk assessment systems for other natural hazards like flooding and earthquakes. So starting to think about how we can develop likelihood and consequence probabilities for wildfire risk, and then link that to modelling of community vulnerability, infrastructure vulnerability, and impacts. So a bit of work done in that space, and hopefully more will be done over the next few years. So again, a huge amount of work in the social space, looking at mitigation of human-caused fires, looking at fire danger communication, looking at case studies of recovery and community response to fires, and also case studies of rural fire communication effectiveness as well. So huge focus on case studies through the social science across a number of fires dating from sort of the Port Hills fire in 2017 right back to the Blenheim fires in 2000. All right, so I also just want to quickly touch on some of the additional operational research that we do. And a lot of that is work that's directly funded by stakeholders due to specific needs being identified by those organisations. And the fire service and now fire and emergency have been a key aspect of that through particularly the Contestable Research Fund, but also other organisations like the Ministry for Primary Industries, particularly around things like climate change. So here we have done a range of activities, including the production of things like seasonal fire climate outlooks, studies to better understand how climate severity varies across the country, what the potential impacts of climate change are on future fire danger, mapping of wildfire-prone areas, economic costs of wildfires, and more recently, just in the last year or so, work around ammunition-caused fire ignitions, the forestry skid site work that I mentioned, and a current project that's linked to the fire plan rollout around developing triggers for declaring fire seasons and other activity restrictions. So yeah, a real wide body of research that gets conducted through this sort of direct funding and interaction with the key stakeholders like fire and emergency. And this is just a subset of the work that's been done over the last 25 years or so. As well as that, as I said at the outset, we also study wildfires and assist with wildfire response. So Veronica would have said that she's provided operational support to incident management teams at a number of wildfires over the past few years. Likewise myself, both here and in New Zealand. Several members of the team are also firefighters, volunteer firefighters, particularly with the High Country Fire Team here in Canterbury. So we're out there working with fire crews, trying to get a better understanding of the sorts of issues that are faced during firefighting operations. And this is where particularly some of the work around new tools and techniques is feeding into the research. I guess I just want to finish up by just looking at technology transfer, and I think right from the outset, one of the key benefits of the fire research program has been this really strong focus on taking the findings and the results from the research and making sure that they are transferred across to the operational sides of the organisations to ensure that that research is picked up and utilised to make changes where they're needed. And as a group, we operate in that tech transfer space right across the spectrum from, as I said, working with fire crews through some of our members of the team that are firefighters, with regular interaction with fire and land managers, incident managers during operational events, through to key fire managers within the stakeholder organisations, local government, right up to, and this is an old slide as you can tell, right up to the higher levels of management within the likes of the Fire Service, National Rural Fire Authority previously, but now Fire and Emergency. So interacting with senior management as well to make sure that they're aware of the research and the outcomes of the research and how they can be implemented. And so what that does is that, I guess, promotes a push from the bottom up in terms of the research and how that research can be used, but also a push downwards from the top in terms of making sure that we're linked into the research and are taking up research findings as well. And to date, that's been very successful, I think. So again, using a whole range of mechanisms for that tech transfer, so things like reports and other publications and wildfire case studies, but also involvement in research workshops and roadshows coming around and talking to fire managers. We have a role in training courses, so right from the very early days and some of the development of the learning resources for some of the rural fire courses like the Fire Weather Index system and the Fire Environment unit standards, through to upfront teaching of things like the intermediate fire behaviour course and other higher level fire behaviour prediction training, and also lecturing to the likes of forestry students and to fire engineering as well. And then obviously the tools developments are also another way in which we transfer the findings from our research into operations. And there's been a whole range of those tools that we've mentioned previously. Our website is also one of the key mechanisms for getting information out there. So if you haven't been and had a look, I'd thoroughly recommend going and having a look and seeing what's there. There's a whole lot of information around the research that we're doing, access to the tools that we're developing and to the publications we've produced, and to other news and events around the program. If you look at some of the tools and resources, these are some of the things that we've just been talking about. So you can access all of that information from the website. We've also recently introduced a web blog, so the Rural Fire Research web blog, which you can subscribe to via our website, and that has brief updates on research activities and new publications, etc. And we've produced a number of those since we introduced that a couple of years ago. And then more recently, we've also introduced a YouTube channel for a series of our rural fire research videos. So you can access videos from our research burns, from some of our other research activities and presentations. So there's a range of videos there that are already up there for viewing. And so if you have an interest in what we've been doing, that's a really good place to start in terms of some of the videos. And that includes some of the footage from our recent research burns as well. So just to finish off, so the Scion Rural Fire Research is a multidisciplinary team. We conduct a wide range of research from the sort of the physical fire environment through human factors and social research. We do practical field-based experiments and case studies. There's a real focus on the application of the research and delivering the benefits right down to firefighters and fire managers through that strong technology transfer focus. And we have a history of really great relationships with the end users that support our work. And I think that's really evident through the support that we get for our research activities like our research burns. So we're really grateful for that and thankful that, that we can tap into that support to help with the research. So that's all I have. So thanks for the opportunity to talk to you about the research program. And I guess, Trent, open to questions if we've got a few minutes, which we don't have too many.
Thank you very much, Grant. Appreciate that. We do have one question here from Bevan. You mentioned using the temperature sensors to monitor when piles were getting hot enough to spontaneously combust. Could this also be used in something like a hay shed or other areas where spontaneous combustion is a risk?
Absolutely, yes. Yep. So this is meant to be designed as a probe that could be, put into the centre of a pile or to a stack of hay or a compost pile, and used to monitor the temperature and just provide regular alerts as to that temperature. And you can watch that build up of temperature over time. So absolutely, that's one possibility. And we're hoping that we can develop these and can produce them relatively cheaply. So it's exactly the market for this type of sensor.
Excellent. Well, thank you very much. We've come to the end of our session. I thank you, Grant, for your presentation today. I certainly enjoyed it, and I got a lot of information out of it. Thank you, everyone, for attending. Thank you, Grant.
Thank you.